All right, thanks for sticking it out to the last talk of the first day of jet lag. So I'm very happy to introduce myself. My name is Anup. I'm going to talk about communication complexity. So my plan is to give a very sort of basic understanding of this topic, which means I really want to make sure that everything I say is understood by everyone. So don't hesitate to stop me, slow me down, and ask questions. So I've also been writing a textbook on this topic with Amir Yehudayov, and you can actually see a draft, a very incomplete draft of the textbook on my homepage. So if you Google my name and get to my homepage, you'll see a link to the book where there are formal proofs of many of the things that I will sort of sketch. So that's a reference for everything I'm going to say, and it has more than that too. So, okay, so what is communication complexity? We'll see some examples in a second when I introduce it. But before I do that, I want to say that it's a really fascinating topic to me because it has a few nice features. One is it's a model that lends itself to really clean and beautiful proofs that come from various parts of mathematics. So there's a role of combinatorics, analysis, and information theory, and all of them give results in this model. And on the other end, it's actually it's very nice in terms of the understanding and theory that you get out of it. But it's also very nice in that it actually seems to have many different diverse applications. So results in communication complexity have led to, in many cases, the best lower bounds in data structures, in problems that you see in distributed computing, in understanding concrete computational models like circuits and branching programs, and also more recently in understanding things in geometry, like the extension complexity of polytopes. Okay, so somehow this one thing seems to apply to many different other models, which for me is a hint that it's something fundamental, and that's why I like studying it. So my plan for the 4 talks I'll give on the subject is I can't cover everything we know about communication complexity, or even hope to try and do it. So what I'll do is I'll focus on this plan. So today I will just give a few examples of some clever protocols to give you a feel for what the different models that that show up in communication complexity. And then I'll try to spend a little bit of time formally defining what two-party communication complexity is and what you can say about two-party communication protocols. In the next talk, I'll talk a little bit about what we can say about the relationship between the rank of matrices and the communication complexity of two-party computation, and maybe start talking about where information theory comes in to understand communication complexity. On the third day, I'll focus almost entirely on results about the relationship between information complexity, or information theory quantities as applied to communication complexity. And on the last day, I will talk about this side of this picture. Okay, how you can use the results here to prove things in many different places. Okay, so let me get started. So what I'll start with is I'll just explain, instead of sort of defining formally the model, I'll sort of informally just tell you, give you some examples of some clever communication protocols, so we just get a feel for what they are. And that'll be, I think, much more efficient than sort of formally telling you what the models are. So the first protocol I want to tell you about is a clever deterministic protocol. Okay, so let me tell you the setup. So the problem looks like this. There are two parties, Alice and Bob, and there's a graph that they both know ahead of time. Okay, so there's a G, it's a graph, and then there are two parties, Alice and Bob, and they get as inputs two subsets of the vertices of the graph. Alice gets a clique C. So Alice gets a clique, namely a set of vertices which are all connected to each other. And Bob gets an independent set I. So let's say this is a graph on n vertices. Okay, so clique means Alice gets a collection of the vertices of the graphs that are all connected to each other, and Bob gets a collection of the vertices which have the property that there are no edges in a set of vertices. They form an independent set. And what they want to know is, do they have a vertex in common? Okay, so what they want to know is there V that's common to both of them? They know G, and only Alice knows C, and only Bob knows I.
Are the vertices, they are like numbered to distinguish the points?
Yes.
Okay.
Yeah, so the vertices are 1 through n, and they know what their edges are. And C is some list of numbers from 1 through n, and I is some list. Okay, so what's a naive protocol for solving this problem? Or what's a protocol? Yeah, so Alice could just say, here's my clique, okay? That would take n log n bits of communication. Actually, it would take n bits of communication in the worst case, not n log n. Yeah, sorry, your comment?
It depends on the graph. If the graph has only one clique, then it's very easy to
It could be any subset of that clique. Right? So, if, for example, if the whole graph is a clique, then any subset is a clique. And that could be Alice's. But then Bob has only a few choices. Okay, so, yeah, you're right, it depends on the graph, but there are it's easy to see that there are graphs where the number of choices for both C and I is really huge. What I'm going to show you is that actually this problem can be solved with log squared n bits of communication. Okay, it's a clever protocol. So here's the idea. So I'll try and get you to guess the idea, but I'll tell you the first step. So if Alice sees, so here's the protocol. If there's some vertex V in the clique, such that the degree of V is less than n over 2, then Alice announces V. Okay, so suppose Alice finds a vertex in her set which has only n over 2 neighbors, then she's just going to announce V. And this helps both of them make a lot of progress. Does someone see why? Yeah, it's on the right line, but actually it's flipped. So the point is that if you look at all the non-neighbors of V, they are not in C, in the clique. So once V is publicly announced, Alice and Bob can discard all the non-neighbors of V. Okay, so that gets rid of half of the vertices. Okay. Sorry, the one thing to check. So if V is in both C and I, they're done. Okay, so if Bob sees that V is also in I, then he says it's also in I, so we're done. But if not, then such a vertex helps a lot because they get rid of n over 2 of the vertices in the graph. And very similarly, if there's a vertex in I such that the degree of V is at least n over 2, then Bob announces it. And for the same reason, if there is such a vertex V in I, then they eliminate n over 2 of the vertices, because all the neighbors of V are definitely not in Bob's set. So Alice can throw them away. Okay? So in this way, they just repeat this until there are no more vertices to announce. How many times can they repeat this? They can repeat this at most, so these steps can happen at most log n times. Because each time, like half the graph is being eliminated. And what happens if these steps do not happen? So suppose there's no V that satisfies 1 or 2. Then they have no common vertex, right? Because all of Alice's vertices have degree bigger than n over 2. And all of Bob's vertices have degree less than n over 2. So they know that they're disjoint, so they can stop. Okay, so each one of these steps takes log n bits to communicate such a vertex, and this can happen only log n times. So you get a protocol with log squared n bits of communication. Any questions about the protocol?
Number 2n is in vertices in the original graph.
There are n vertices in the original graph. Good. So actually, yeah, you're right. So at each step, I need the n to be changed to the number of vertices that are left. Okay, good. Yeah. Yeah, so I should write here the number of vertices that are left. But I'll leave it. Okay. Other questions or clarifications? Okay, so there are a few takeaways that I want to, the reason I showed you this. So in this protocol, it takes log squared n bits of communication total. And this protocol is sort of inherently interactive. Okay? It's not one message from Alice to Bob. They have really a conversation, and the things they say depend on each other. Right? Because in every step, they're throwing away vertices, which changes the graph. So the messages sent depend on the previous messages. Okay? And in fact, you can show that if you tried to solve this without interaction, you would need a lot more communication. Okay? So kind of the interaction is crucial here. So that's one of the things that we want our model to capture. We wanted to capture interaction.
Do you mean some formal statement about this?
Yeah, so actually you can prove that if the protocol is restricted to Alice just sending one message.
For some graph, right?
Yes, for some graph. Yes. Then it cannot be so efficient. Okay, and yeah, so we know many examples of such problems which you cannot solve with a constant number of. In fact, we know that there are problems which, with 10 rounds of interaction, you can solve them very efficiently, but with 9 rounds, you require an exponential more amount of communication for every 10 and 9. So for every k, you can solve it with k rounds, but not with k minus 1 rounds. Okay, so that's one example of a deterministic protocol. And now I want to give you another example. So now I'm going to change the model a little bit. I'm going to allow randomization and tell you about a couple of protocols. The first one is for equality. So Alice and Bob are given 2 n-bit strings. So Alice has X, it's an n-bit string, and Bob has Y, which is an n-bit string. And they want to know, is X equal to Y? Okay, so here you can show that actually if they want to solve this problem deterministically, so if they're just going to send messages that are deterministic, then they can't do anything that's not trivial. The best they can do is to send the entire string across. Any solution will involve at least n+1 bits of communication. Okay, so it's really the only thing you can do. But now I want to show you that if they're allowed to use randomization, they can do much better. Okay, so here's the idea. So they will pick a random string z that's an n-bit string. Okay, and Alice will send sum over I, just the inner product of x and z, mod 2. Just a bit to Bob. Okay, so just a bit, which is the inner product of x and z.
They both have access to z?
They both have access to z. Okay, so Bob is here, and Bob can also, using his eyes, see z. Okay. Okay, so Alice will just send 1 bit, and now I claim that this bit is very useful because what should Bob do? Bob will compute this, right? Sum over I, yi, zi, the inner product of y and z, mod 2. And if x and y are not the same, then these two will be independent, right? And so the probability that they will be equal is a half. Okay? So if x and y are the same, then definitely these two bits will be the same. But if they're not the same, then these two will be independent bits. So by repeating this experiment 10 times, they can be very sure which case they're in. Okay? Okay, now to address the issue of, okay, they had to assume that they have this common z, but it turns out that you can actually get rid of that. You can, it's a little more complicated, but you can actually have, you can first reduce the length of z to be just log n bits and produce a similar experiment. And once it's reduced to log n bits, you can just have Alice send the sample of z. So Alice can privately sample z, which is log n bits long, and send it along with the inner product of x and z. Formally what will happen is actually Alice will send sort of an ID, which is of length log n, that determines a string z that you're supposed to take the inner product with. So, okay, so you can actually solve this problem also with just log n bits of communication without any common randomness. Okay, so that's one randomized problem. That's A. And now I will do B. So B is a little more sophisticated, but it's using essentially the same idea. So again, Alice has X, and Bob has Y, which are strings. And what they want to do is they want to find the smallest I where X and Y differ. Okay, if such an I exists. So either they should output that X and Y are the same, or they should find the smallest index where Xi and Y disagree. And it turns out you can also solve this problem with log n bits of communication. So you can do order log n communication using a randomized protocol. And the idea is, well, it's easy to get polylog n using this idea. What you can do is you can do binary search. So they can kind of compare the first half of the strings, see if they're equal or not, using this idea. And if they're equal, then they know that the solution is in the second part, so they reduce the space by a factor of 2. So they keep doing this. If they do that, they'll kind of need to exchange log n bits. They'll actually need more than log n bits of communication because there'll be log n rounds, and they'll have to ensure that the probability of error in each round is sub-constant, so that there is no error anywhere. So that requires a little more than log n bits of communication. But there's a clever way to do this and somehow amortize the error so that the total communication is actually only order log n. Which you can think of. So if you just do the naive idea where you kind of exchange hashes and do binary search, then I think you will get a protocol with log n times log n bits of communication. Okay. All right, so next I want to tell you about another problem that admits a randomized solution. That's actually a really clever protocol due to Hassad and Richardson. And this is for computing whether two sets are disjoint or not. Okay. So suppose Alice and Bob, so I'll write here. So suppose they're working with the set. Okay, so this I just mean the numbers from 1 to n. I write this. And what happens is Alice has a subset X of size k, and Bob also has a subset Y of size k. And what they want to know are X and Y disjoint or not? So is X intersect Y empty? Okay. So how many bits of communication does the naive protocol take? Or what's the naive protocol? K log n, yeah. Yeah, if k is small, it's like k log n. In general, it's log of n choose k. You just say which of the sets you have. But I'm going to show you a protocol that actually takes only k bits of communication. So it saves this log factor. Okay, and again, it's going to be a randomized protocol. You can show that if you're doing this deterministically, k log n is the best you can do, or log of n choose k is the best you can do. But with randomization, I'll show you a protocol that just takes k bits of communication. So this is a protocol due to Hassad and Richardson. And here's the idea. So again, I'm going to assume that we have access to a long string of common randomness, which can be got rid of if we, with a small change in the complexity. But I'll assume that we have it. So what is the randomness going to be? It's going to be a sequence of uniformly random sets in this universe. Okay, so there will be sort of a random tape here, which will contain sets Z1, Z2, etc. Okay, just an infinite sequence of random sets, which are all so just uniformly random subsets of 1 through n. And what Alice will send she'll send the index I. So she'll send the smallest number I such that X is contained in Z sub I. So she'll send the smallest index I such that x is contained in z sub I. And then Bob will do the same. Okay, so Bob will send so smallest. They're completely random sets. So every element is included with probability half, and this is done independently.
But they have to be bigger than k for that to happen.
Yeah. Yeah. So Bob will send the smallest j such that y is contained in z sub j. Okay. So that's the basic idea of the protocol. And now let's see. So I claim that this actually is a lot of progress in every step. So let's forget about how much communication it takes to do this. So what happens if you know a random set that contains x? What information does that tell Bob? Well, at least when x and y are disjoint, it says a lot, right? So imagine that x and y were disjoint. So x is here, and y is here. And now Alice is basically announcing a random set containing x. So what can Bob do?
Yeah, you're going to have like two covers for your sets, and if you were to draw the zi and the zj, they would be covering, and you could try to see by there how many points they have in the intersection.
Let's forget about the second part. Something even happens with just the first step. Yeah, exactly. So Alice announces, this set zi. Bob can throw away all of these points, right? She knows, Bob knows that these points are not involved in any intersection. So he can just throw them away. And how many points do you expect to be thrown away? Half of the points, right? So if x and y are disjoint, half of Bob's points will disappear after this announcement. Okay, and the same for Alice. So that's really good. So the number of rounds where this can continue is at most log k, right? They have sets of size k, and in every step, half the points are going away. Okay, but we're not going to do something. So I'm not going to do the analysis very carefully, but I'm going to tell you the intuition. So I promised you just a k-bit protocol. So the point is that if you look at now let's worry about what is the actual complexity of sending this number I. So what you can show is that the expected number of bits you need to send I, the expected value of I will be roughly 2 to the k, right? Because the probability that a random set includes x, it's exactly 2 to the k. So in expectation, you have to wait 2 to the k steps before you find this I. So it takes like k bits to specify I. Okay. So it takes k bits for Alice to send this first I, and k bits for Bob to send this first j. But then after that, the size of the set shrinks by a factor of 2. So in the next round, it's going to take k over 2 bits to send the next index. Okay, so the communication complexity looks like k bits plus k over 2 bits plus k over 4 bits. So it's a geometrically decreasing sequence. And the sum is order k. Okay. So, polynomial.
This seems to require some going over these 2 to the k sets z1, z2 for the party.
Oh, no. As far as I know, this is the only thing that's known. In fact, this is a really interesting protocol because I told you I didn't prove it to you, but there's no deterministic protocol that achieves this kind of performance. Okay, and this is a randomized protocol, but this protocol actually, you can show it has no error. It never makes a mistake. Okay, so it's a randomized protocol that never makes a mistake, but it achieves, because the thing is that, so what's going to happen, actually to make sure that it has no error, you have to modify it slightly. So this was in the case that x and y are disjoint. So if x and y are disjoint, what will happen is eventually one of the sets will disappear. And that party will say, now I have nothing, so we're definitely disjoint. If x and y intersect, eventually what will happen is they'll be left just with the intersection. So you also need to throw in some step of every once in a while, Alice or Bob will announce a random element in their set. Okay, and that will be a witness to the fact that they intersect. So in both cases, you can conclude the protocol when you're sure that we're either disjoint or intersecting, and both things will happen when order k bits have been communicated in expectation. Okay. Yeah. No, okay, yeah, there are some details. So what ends up happening is that you'll only do the announcement when the universe gets small enough. And you don't have to worry about announcing until the sets themselves are dense in the universe. Okay, so there's some, yeah.
The price to pay is to share the information, which is the sequence of...
Yes. Yes. This is a price to pay. You can get rid of this by making it k plus log n. So if you're with k plus log n communication, you can even get rid of this, which I won't tell you how to do it, but there's a way to do it. Okay. So actually, in general, there's a generic result, which says that if you have any randomized protocol that uses a shared public random string, which has arbitrary length, you can get rid of, you can always assume that that string is of length log n, where n is the number of bits that the players have as input. Okay? Essentially, the idea is what you can do is instead of using this random string, you can sample like n to the 100 candidate random strings, which have the property that taking one of those n to the 100 strings is enough, instead of a uniformly random string. And then, so that's your sample set. You can kind of reduce the complexity of the number of bits here to log n, always. But the protocols look much cleaner when you have these, as you see. Okay. More questions or comments? Okay, so that's all. So now I'm going to do one more model that shows up in a lot of proofs. I'll do an example of it. And then I'll try to spend a little bit of time defining deterministic protocols formally so we can understand really what we're talking about. Okay, so this model is called the number on forehead model. And it makes sense only when you, or it's interesting when you have more than two parties that are communicating. So let me give you an example. So imagine that you have Alice, Bob, and Charlie. And each of them has a number, an input, from 1 to n. Okay, so Alice has x to n, Bob has y from 1 to n, and Charlie has z from 1 to n. But they actually don't know these numbers because these numbers are written on their foreheads. What they know are the numbers that are written on the other players' foreheads. Okay, so Alice knows y and z, Bob knows z and x, and Charlie knows x and y. Okay. And okay, so what's the problem that I want to study here? So let's consider the example where they want to know this. They want to know if x plus y plus z is equal to n. Okay. So they want to know if this sum is equal to n. So what is the complexity of the trivial protocol?
Each one can announce, or someone can announce the sum of the other two.
Someone can announce. You actually don't need to do that. All you need to do is tell Alice this is what's on your forehead.
Yeah, no, that would be each one
Yeah.
announce what he sees.
Yeah, so just have Bob announce x.
But you could already announce the sum, no? It would be better if you want.
Well, but nobody knows the sum.
No, Alice knows the sum of Bob plus Charlie.
Uh-huh.
He could already announce the sum.
Yeah.
And then just someone else would need to say,
Yeah.
talk about Alice.
Well, in terms of complexity, those two solutions are the same. Either way, you're going to send log n bits, right? So either, yeah, so Alice could announce y plus z, and then Bob can check whether this happens. Or Bob could just announce x, and Alice could check. Okay. Both of those solutions take log n bits of communication. And I'm actually going to show you that you can solve this with order square root log n bits of communication. It's going to be deterministic, yeah. Okay, and in fact, so it's actually connected to an old problem in combinatorics, and in fact, understanding this is essentially equivalent to understanding that problem. And that problem is, how large a set can you have that is free of arithmetic progressions? Okay, so let me tell you how to use such a thing. So first, let me tell you a theorem from arithmetic combinatorics, and then I'll show you how to use it. So the theorem is, there's a set, actually I need something stronger, so you can color the set of numbers from 1 to n with 2 to the square root log n colors. Such that for every arithmetic progression, so for every a plus b, a plus 2b, they're not monochromatic. Okay, so all three are not the same color. Okay, that's a theorem. It was proved by Behrend, 1928. And now I'll show you how to use it to get a protocol. The proof of the theorem is really beautiful, but I think I won't have time to do it. But I'll just show you how to use it to get a protocol. And that's really simple. So here's the idea. Consider the numbers. So consider x prime, which is n minus y minus z. This is a number that Alice can compute. This is Alice's idea of what should be on her forehead if the sum is equal to n. Okay, similarly, Bob can compute y prime, which is n minus x minus z. And this is what should be on Bob's forehead from Bob's perspective if the sum was equal to n. And let's, so consider, so note that x prime minus x is equal to n minus x minus y minus z is equal to y prime minus y. Okay. So the point is that Alice's estimate is off by exactly the same from Bob's estimate, whatever that is. And they basically want to know, are these quantities 0 or not? Okay. So here's what they will do. What Alice will do, Alice can compute x prime. So Alice will announce the color of x prime plus 2y. Okay, and what Bob and Charlie will do, we'll check that this is equal to the color of x plus 2y, which Charlie can compute, and the color of x plus 2y prime, which Bob can compute. Okay? Now, I claim that the only way that these three colors are the same is if the sum is equal to n. Okay? So there are two cases here. Because x prime minus x is equal to y prime minus y, if this quantity is 0, right, if n minus x minus y minus z is 0, then all three numbers here, x prime y will be the same as xy will be the same as xy prime. Okay, because y prime will be the same as y and x prime will be the same as x. So in that case, they'll definitely be outputting the color of the same point. So they will definitely be the same. Now in the other case, if they're not the same, if this is non-zero, then I claim that these three numbers form an arithmetic progression. Okay, indeed, you can write, this is x plus 2y, and the second term in the progression is x plus 2y plus x prime minus x. Right? That's x prime plus 2y, and the third term in the progression is x plus 2y plus 2 times y prime minus y. And y prime minus y is equal to x prime minus x. So this is 2 steps. Okay. So those three numbers form an arithmetic progression. And by the property of the coloring, they cannot have the same color. So in this way, this coloring gives you a protocol with square root log n bits of communication, because that's how many bits you need to specify the color. And what's interesting is that the reverse direction also holds. Any protocol for this problem must give such a coloring. Okay. Any protocol. So the protocol may have some other structure that doesn't look like this, but nevertheless, you can use it to get a coloring of the numbers. So this problem looks intimately tied to this problem of finding colorings of numbers. Yeah? Yeah. So there's some. So it turns out. So if you want. So this one also does not have monochromatic 4-term APs because that contains the 3-term. But you can find even fewer colors that avoid monochromatic 4-term APs. And I don't remember what the dependence is. And that should also give better protocols for 4 players here. But I don't know. I don't think anyone has worked that out, that dependence. Yeah?
What is the complexity of the algorithm which will color the graph?
It's actually very, I can tell you the colors. So no, I can't tell you the colors, but it's very efficient. The color actually, it looks like basically you take this number, x plus 2y, write it in base d, where d is like 2 to the square root log n. Okay, so that's some representation. View that vector as a vector, like the digits as a vector, and you basically announce the length of the vector. That's the basic idea. Okay, that turns out to be the coloring that works. So Behrens' basic, the counterexample, it's a really beautiful example if you want to find a set that avoids arithmetic progressions. It basically is a set of numbers that have the same L2 norm when they're viewed as vectors. And the fact that it avoids progressions corresponds to the idea that you cannot have 3 collinear points which have the same L2 norm. You can't have 3 points on the sphere which lie on the same line. Okay, that's the proof of correctness. Okay. Any more questions? Potentially it could help, but I don't know how to use it. Actually, sorry, I take that back. Sorry, this problem, yeah, there's an obvious. So maybe I'll ask you. How could you use randomization to solve this problem? It's the same thing. So, I mean, what does Alice want to do? Alice just wants to check that whether x prime is equal to x. She knows x prime. The other people know x. So she just asks Bob, send me the inner product of x with a random vector, and then checks that the inner product is consistent. Okay, so that would work. But so that give you a constant or log n bits of communication. But yeah, so for this problem, the interesting case is when it's deterministic. More questions or comments? It would take log n. Yeah, it would take log n. And for deterministic protocols, the best lower bound we have here, so this is a protocol with squared log n bits, and the best lower bound is like log, 3 logs. Log n bits. Okay, so there's a big gap, and this gap corresponds to basically our understanding of how dense a set can be before it avoids arithmetic progressions or not. All right, so those are some examples. In the remaining time, what I want to do is focus on just deterministic protocols. And I want to basically understand how to define them. And then once we define them, we'll see kind of visually what are they really doing to the space of inputs. And that's something that's really helpful when you want to try and prove that when you want to prove lower bounds against protocols, when you want to prove that there are no efficient protocols. Okay, so let's see. So I'll start here, I guess. So what is a communication protocol? So we saw a bunch of examples, but now let me define it formally. So a protocol, so these are deterministic protocols. And I'll focus just on two-party protocols. Okay. So say Alice gets x that comes from some set, and Bob gets y that comes from some set, and they want to ahead of time decide how to interact with each other once they have the set. So the way I'll define a protocol is using a binary tree. Okay. Where every vertex, so it'll be a tree like this, and every vertex will be labeled by a function that maps one of the player's inputs to a bit. Okay, so say this vertex is labeled by a function f that maps the space of inputs of Alice to a bit, and maybe this vertex is labeled by a function mapping Bob's inputs to a bit, and so on. Now, how do you run the protocol? Well, you start at the root, and you basically evaluate the functions and transmit them. So you start at the root, and Alice sees, so they know this specifies the protocol. So everybody, this is like the code of the protocol. So everybody knows this description ahead of time. Then they get their inputs, and Alice looks at the root and sees that it's her turn to speak, because it's a function mapping her input to a bit. So she announces f of x, okay? And suppose it turned out, f of x, her input, is equal to 1. And that means that they should go down to the right side of the tree. Okay, so they go down to this node. And now they're at this node, and Bob has a function labeling this node, so it's Bob's turn to speak. So Bob will evaluate g of y, and maybe g of y is 0. So they'll go down this node. Okay? So that's a protocol. So at the end, they will reach a leaf. And when they reach the leaf, they're supposed to know what the protocol computed. The leaf is basically the computation of the protocol.
G is a function from y and n.
Implicitly it is, but that's captured by the fact that you know which vertex you're at. Okay, so it's just a function of one of the inputs, but the choice of the function depends on the vertex, so it holds that information. Okay, so that's a protocol, and all the deterministic protocols we talked about can be described like this, right? It would be painful to describe them bit by bit, but we could, in principle, do it if we wanted to. And what are we measuring here? What we've been measuring so far is sort of the length of the longest sequence of bits that could be transmitted, which is just the depth of this tree. Okay, so the complexity is so this depth is the communication. So what we've been trying to do here is find the protocols that have the smallest depth. Okay. All right. So once we have this view, I can tell you a little bit about what the protocol does to the space of inputs. Yeah.
How do you describe the tree to communicate a random vector?
So in the case of randomized protocols, you imagine that Alice and Bob also have a random input. So f will be a function of both x and the random input, and then g will be a function of y and the random input. Okay, so they're just running these functions. It's again a deterministic thing, but they have the random a third input. But then you have to talk about when is it correct. So you want that there are a couple of complications, like should you define the protocol to be correct for every input or for an average input? And all of these things make sense. Okay, so there are some choices you can make. But we won't get into that for now. So let's sort of do a visualization of what happens when you run the protocol on an input. That's the last thing I want to describe. So suppose you have the space of inputs, x cross y, and I'll arrange them in the form of a matrix. Okay, so let's say, here are all the y's, and here are all the x's. And in the entries is the output that you're trying to compute. Okay, like the values you're trying to compute. So one way to visualize the computation is that Alice knows kind of which row they're interested in this matrix, and Bob knows which column, and they want to compute the xyth entry of the matrix. Okay, that generically describes all the computations we've been talking about. Now, what does the protocol do? So let's say Alice's first function is f. Okay, so what that corresponds to is a partition of the rows into two sets. Right? Those that get mapped to 0 and those that get mapped to 1. So imagine that this is that partition. So all of these, for all of these rows, Alice will send a 0. And for all of these, Alice will send a 1. Okay, so this is what the first vertex in that tree does. Now if you look at the first vertex in the second level, there are two vertices. And both of them correspond to partitioning the columns of the matrix. Right? Because Bob is going to send a function of the name of the column. So if you look after two levels, what's going on is this. Or I guess I went 2 depths down. But if there are 2 transmissions, then the 4 vertices at depth 2 correspond to these 4 pieces of the inputs. And in general, every time you look at the protocol tree, then what it's doing is it's splitting one of these rectangles into two pieces, either horizontally or vertically. So what the protocol tree ends up doing is, something like this. Okay, it partitions the entire matrix into a bunch of rectangles. Okay? And when is the protocol correct? For the protocol to be correct, it means that at the end of the protocol, the parties have to know what is the value of the thing they were trying to compute. Which means that each one of these pieces has to be monochromatic. Right? Like this entry, if the protocol, this is the leaves of the protocol tree, here you must have either all zeros or all ones if the function you're computing is Boolean, or so this is what it looks like. So the protocol kind of corresponds to a partition of the matrix into monochromatic rectangles. Okay. And if you have C bits of communication, what you get is 2 to the C monochromatic rectangles. Okay. And that's really nice. So once you see this, you think, okay, maybe a cleaner abstraction to think about is we just want to know, what is the smallest number of monochromatic rectangles that you can partition the matrix into? That's a different measure of the complexity of the matrix. Okay, the smallest number of monochromatic rectangles that you can partition. Okay, and one thing the first thing that might occur to you is, are these two measures the same? Like, is this the number of monochromatic rectangles? Essentially, does that determine the communication? And it's not quite the same, okay? In fact, this is something that people have made a lot of progress on recently in the last few months. But here's one example to think about. So let me partition this matrix into these monochromatic rectangles. Okay, so that's a bunch of monochromatic rectangles. And there's no way a protocol did this, because there's no horizontal or vertical line anywhere. Okay, so it's not true that every partition into monochromatic rectangles corresponds to a protocol, because this can't be generated by a protocol. Okay, nevertheless, what you can prove, now we'll try to sketch the proof very quickly. So this says that if you have a C-bit protocol, you get 2 to the C monochromatic rectangles. And here's a theorem. Two to the C monochromatic rectangles. So if you can partition the matrix into 2 to the C monochromatic rectangles, then you actually get a C-squared bit protocol. Okay, and moreover, recent work has shown, I think the last paper in the series is Kotari. This is tight. This is the best you can do. Namely, there is a matrix which can be partitioned into 2 to the C monochromatic rectangles, but there's no protocol which has less than or significantly less than C-squared bits of communication. Okay, and that's very recent. Actually, nailing it down, there's some error terms here, so I think it's still, I don't feel like it's completely understood yet. But it's been a lot of progress. So let me show you this thing, which was proved by Lovash, I think is the right credit. It's kind of a cool protocol. So what I'm given now is, I'm just given, so I have a matrix and there are 2 to the C rectangles that partition it. Okay. Now it's a bunch of rectangles, and they're monochromatic. And the parties want to use this partition to actually compute the value of the function. So what does Alice know? Alice knows an x. So Alice has this. So Alice sees a bunch of rectangles that are consistent with her x, right? But she doesn't know which one is the right one. If she knew which rectangle contained both of their inputs, they would be done, because the rectangles are monochromatic. So once you know which rectangle you belong to, you know the value of the function. Okay, and Bob knows y. But again, Bob sees a bunch of rectangles. They're basically trying to find the rectangle that contains both x and y. This is the rectangle they want. So here's the idea. Suppose Alice announced Suppose Alice announces this rectangle. Then what can Bob do? If there's a rectangle that lies below this one, then Bob knows that's no longer relevant, right? So if Alice announces this, then Bob can discard this. Yeah, in a second. Yeah.
What do you mean by Alice announces this rectangle?
Ah, good. So there are 2 to the c monochromatic rectangles that they both have. So Alice can just say the name of one of them. She can say, here's a rectangle from this list that's consistent with my input. And that's some information for Bob. For example, if Alice says, this rectangle is consistent with my input, Bob knows that this rectangle is not consistent with Alice's input because they're disjoint in the set of x's that they share. Okay, so he can throw this away. Okay. Now, and they both know that. So when Alice announces this, she knows that Bob will then throw this away. So what we're going to do is we're going to show that there's a way for either Alice or Bob to announce the name of a rectangle, which will result in half of the rectangles being thrown away. Okay? And that will give the c squared. So in each round, one of the players will announce a rectangle, and this will take c bits. And then they will do this at most c times. I'll guarantee that this announcement will eliminate half of the rectangles in the picture. And then they will do this c times, at which point all the rectangles will be eliminated. Okay, so they'll have to stop before then. No, c times, because there are 2 to the c rectangles. Okay, so that's the high-level goal. Now I want to tell you why there has to be this rectangle that eliminates a lot of rectangles. Well, let's look at the real rectangle. Okay, so let's look at the real rectangle that Alice and Bob have. This is the one that contains their input. Okay. Now, every other rectangle, it can be, this is a rectangle that's bad for Bob, in the sense that if Bob announces this rectangle, it doesn't eliminate this. Okay, but it's good for Alice. So every other rectangle can either intersect this rectangle horizontally or vertically, but not both. Okay. So that's the key point. So if you look at every other rectangle, you can have a rectangle that intersects this rectangle horizontally, or a rectangle that intersects it vertically. But you cannot have a rectangle that simultaneously intersects this rectangle both horizontally and vertically. So in particular, if Alice announces this rectangle, either Alice or Bob can use this rectangle to eliminate half the rectangles. So there's always one rectangle that eliminates half of the rectangles. So now they may not get the right rectangle, but in every step, Alice or Bob is guaranteed to find one rectangle that eliminates half of the rectangles, because the correct rectangle has that property. Okay, so that's the proof. So in each step, they announce this rectangle. It takes c bits to announce it. And you have to do that c times before you eliminate all the rectangles. They both, so Alice will say, either will say, here's a rectangle, will say, I don't have any rectangles. And then Bob will say, so if you want to do a formal protocol, Alice will be either sending no rectangle or yes rectangle and name of the rectangle. Okay, and then Bob will be speaking similarly. Other questions or comments? Yeah. Yes, it's actually very, very close. You can think of I think this actually gives, so I'm trying to think, I think this is a special case of that, is it? I think there's a way to view a graph here which has, Alice has a clique and Bob has independent set, but I don't remember exactly how.
I think this is the special case of the other one. So I think
this is a special case of the other one?
Yeah.
Okay.
I thought that you had a partition by considering on which point the clique and independent agree. Because if they agree, and if they intersect, they can intersect at most one point.
Mm-hmm.
So there are 10 rectangles. So C would be
C is log n. Okay, so each rectangle corresponds to a vertex.
yes.
And
But they're not disjoint.
So I think you can.
the rectangles are disjoint in this. Yeah, do you remember how it works?
So I think you just like connect. So each node is a rectangle,
Uh-huh.
and then let's try connecting things which share a horizontal line.
Oh, which connect horizontally. Okay.
So then do a clique.
So Alice has a clique and Bob has an independent set.
Yeah.
Good. Yeah. Yeah, exactly. Yeah. Yeah, so it's the same problem. So maybe that would be a better way to explain it. Yeah, so one other observation. So here we assume that that it was actually a partition into rectangles. It turns out that you actually don't need the sets to be disjoint. In fact, as long as you have 2 to the C monochromatic rectangles, even ones that overlap, the same argument would work. You just have to be more careful. Alice will announce a 0 rectangle, and she will try to eliminate half of the 1 rectangles, which have to be disjoint from the 0 rectangle. Okay, and you can work that out, and a similar argument works. And as I said, this appears to be best possible. I think this lower bound says the counterexample has a c to the 2 minus some small constant, or small little o of 1 maybe. Might be still possible to improve that to show that it's really tight. Okay, so I'll stop there. Thanks.